So never expect to have the semester start so fast. Initially, I thought our semester started by next week, but somehow I just got to know that our semester start today. Okay. So welcome to the class. So this is a BTE4013 Microelectronics, and I believe most of you are under the electronic streams. So this subject is under electronic. So if you somehow enter the class wrongly, please let me know so I can kick you out. Okay. So okay. So who's the course rep here? Can anyone tell me who's the course rep?
Good morning, sir. I'm here. I'm Coursework
Oh,
here.
okay. GA is here. Okay, okay. So later Yong Wing Liang, please stay back for a while after the class. I need to discuss something with you. Okay. So this is a microelectronic and I'm the lecturer, Dr. Go KM. Some of you may have known me earlier. So if you have anything you want to ask, just feel free to email me at trc.edu.my. Okay, Dr. Go KM. And I believe most of you are the electronic stream, so that's why you have to take this subject. I think this one is an elective, if not mistaken. Okay, give me a moment. I check something first. Okay, let's continue. So this subject is BTEE 413 Microelectronic CRO Microelectronics. So as you know, this is a 3 hour subject, 3 hours lecture per week. 3 hours lecture per week. Then you have a 1 hour tutorial alternative. And then you got a two practical lab. This practical lab is to use the software to do it. So you don't have to go back to the campus to do anything. Okay. And these two practical hours is for 4 weeks. If not mistaken, it starts at week 3, week 5, week 7, and week 9. Okay. Depends on your group. Okay. So if your group, let's say if you are in the alternate group, you may have a 4, 6, 8, and 10. Because the number is quite still okay. There are 30 students here. So you might be split into the different week. Some of you may have realized that there are some problems with your timetable regarding this subject. Okay. I have already informed the staff regarding this. So they are fixing it right now. Okay. Please let me know if you're still having the problem. So as I mentioned, 3 hours lecture, 1 hour tutorial, and a 2 hour practical start from week 3. Okay. So this one alternative is depends on which group are you in. Some of you maybe is in the odd week. Some of you might be even in the even week. Okay, so this is a microelectronic and all lectures and the practical and the tutorial. But some of you may ask, what is microelectronic about? So in this microelectronic, you are going to deal with a little bit of the physics, a little bit of the chemistry also. But don't worry, I'm not going to ask you how to do all this like I won't ask you to do what like sodium chloride, add chlorine, that will become what something like that. That one is not our expertise. But why are we going to deal with the chemistry? Because as you know, sometimes last time when we are learning about the atom, we got the nucleus, then the positive charge and the negative charge somewhere around here, the electron somewhere around here. We are going to do something like this a little bit. And also it involves a lot of calculation. And what I can say is, in this subject, almost 90% are calculations. Okay. Why is it calculations? Because right now we all are in the online mode. So we eventually have to pay more focus on the calculations instead of all the theory. What about all the, let's say, definition or derivation you might ask? Yes, it will involve, but just a little bit, nothing much. Okay, so this is the two main things you are going to know. Physics and chemistry before you go into this. And also, this will somehow will involve something like diode, resistor, or even the transistor. When we are talking about transistor, we learn about the NMOS or PMOS, all these things. This thing we are going to deal with it. Okay. So far, this is what are we going to learn. But when we are talking about the diode, resistor, and transistor, it's not just ask you to do something like the V equals to IR. It's much deeper. Okay. Something like a diode and the transistor, we are going to learn deeper instead of just applying the formula to get what I want, what we want to need. In this stage, any question? If no question, then I should proceed. If you have no question, then type a no in the chat box so that I can know that instead of just waiting here. Okay, I believe there's no question. So let's talk about our chapter. Oh, sorry, not chapter. The basic, all the component in the microelectronic. Okay. So I believe you guys already went through 3 years or 4 years in TUC. So all we need to do is to know what is the learning outcome. Excuse me. So course learning outcome. This thing we need to know. What is course learning outcome? Which means that after throughout this semester, what are you going to learn from this subject? Okay. Very first, explain the theory of the semiconductor, solid state, and the quantum mechanics. When we are dealing with all the microelectronic, we are actually dealing with the semiconductor. When we are dealing with the semiconductor, we must deal with the electron and holes. I believe you guys know, right, what is an electron and what is a hole. In short, this is a negative charge. This is a positive charge. This one I don't have to explain. You guys should be familiar with that. But when we are learning about the electron, we need to know how it flows. Okay? How it flows. For example, what is speed? What's the acceleration? Or even we need to know what's the concentration. Or what is the energy we need to provide them to jump, to make it flow. Okay? But when we are dealing with all the speed, acceleration, concentration, energy, actually we are dealing with the quantum mechanics. Okay? So that's why this is where the physics coming in. Okay, when we're dealing with physics, the most important thing is, for example, kinetic energy. How are we going to learn? How are we going to use? Half mv squared. Or, but this one is dealing with the electron. Then how is the electron move? We may be dealing with E equals to mc squared, all these things. All these things will be considered and will be learned in this subject. Or even you need to study about the momentum, P equals to mv, m is the mass, v is the velocity, all these things. All these are related to the quantum mechanics. And in order for you to learn about the quantum mechanics, this content is covered from the lecture 1 to lecture 2. And the PO that he hit is the PO1, engineering knowledge, which means you are going to learn about the basic knowledge on how the electron move in the semiconductor. This is the PO, CRO1. Then after the CRO1, if the thing is moved, if the electron is moving, means there's a current. Okay, electric current. When there's an electric current, there must be the electrical properties. For example, all the ampere, all the, let's say, voltage, then how is it going to deal with all the current and the voltage or whatsoever thing? Okay, but in order to have the current properties, we also need to know what is the concentration of the electron, because it's somehow related to the value of the current and the velocity also. So that's why in the ClO2, we are going to analyze the solid state operation and the electrical properties of the semiconductor devices. And this thing will be covered from the lecture 3 until the end, because we are going to deal with the semiconductor. When we are going to deal with the semiconductor devices, we need to know about the properties of a resistor, diode, then maybe also even the MOSFET. All these things we need to know that, because all these components are the most basic thing in the microelectronic. And then this is a PO2, thermal analysis. In order for you to hit the PO2, you will be dealing with many of the questions. For example, he asks you to calculate the energy for one electron to jump from one side to another side. Okay. In order for you to do this, you need to know how to analyze the problem. So that's why you hit about the PO2. So you can know that actually the CO1 and CO2 are actually coming from the lectures. Then CO3 and CO4, we are going to deal with the design semiconductor devices with the given IC technology file. What is it? So let's see the next slide. This one is the thing that we are quite familiar. For example, the semiconductor that you can use solution in maybe your breadboard or maybe in your PCB design. But inside that, actually, it involves a lot of the circuit. All these circuits are actually the transistor. Okay, transistor, and somehow actually this is the logic gate. Okay, this is the NAND gate if I'm mistaken. So actually, this one consisting of about maybe 1, 2, 3, 4 transistor, and this 4 transistor and can give you a logic gate. Okay, so in order for us to know how to design this logic gate, we need to know how to design this, all the colorful one. To know how to design all these colorful items, this one is based on our CO3 and CO4. Okay, and you can see that CO3 is actually based on the PO3. You are given one situation, for example, you were asked to design a, let's say, NOR gate, 3-input NOR gate. So how are you going to design it? So you need to design, this one is from the CO3. Then this one is a CO4. CO4 actually hit the PO5, which is the to see whether you can use the modern tool or not. So which means that you need to use some of the software to handle it, to handle the CO3. Okay, what you can see is CO3 is more on whether you can design something. CO4 is whether you can handle a software. This is the difference between these two. And the last two items are actually based on your lab practical. Okay, in this stage, any question? If no question, type a no there. What about the rest of you? Okay, cool. Looks like everyone can understand this. Okay, let's proceed. So let me write here. ClO1, ClO2, ClO3, ClO4. So this one is for lecture L1 to L2, L3 until the end. So this one is from the practical class. Okay. So also this will also included in the tutorial and your examination. And also maybe your assignment is somewhere around here, particular actually. So don't worry about it. Okay, let's proceed. So you may ask, what is the coursework? Okay, so in this work, in this course, so there are actually two coursework only. One is the online test. So okay, sorry, here's something wrong here. So this one should be a 40, should be 60. Okay, I will amend it later. Okay, to give you a final confirmation. Last time there are three components. Last time there are one individual assignment, but somehow this assignment is already integrated in here. Last time is three components, right now only two components. Okay. So on the test, hopefully can be given by week 6. Then lab report is depends on the end of the lab. So for example, in your lab, maybe your last session is week 3, week 5, week 7, week 9. Then your week 11, you can submit. Okay. Then if you're alternative week 4, 6, 8, 10, then your week should be week 12 to submit. Okay. So duration there's a 2 week. So software. What kind of the software are you using in this course? Okay, there are two software you are going to use. One is electric, another one is LT Spice. So this electric, actually the function is to draw the layout and the schematic diagram of the circuit. For example, this and this. Electric, it can use this and this to draw it. Sorry, electric can draw this and this. Then the LT Spice actually is one of the platform for you to measure the waveform. In the other word, it is the place for you to check whether your circuit is designed correctly or not by putting a waveform. Just for example, if you are given a NAND gate, you are trying to design a NAND gate. If you want, okay, and this one is a 1, right? Then even is 0. Then your result will be 0. Then you can use the LT Spice to see whether the result is correct or not correct. Okay, this is the purpose of the LT Spice. And this link will be, this slide will be uploaded into your Google Classroom later. So before you go to your lab, please download these two software. This one is in the Java file, and this one is in the ESC file. And these two are actually the free software. You just use it, okay, without paying anything. Don't worry about it. And then next one. So link for the lab manual or the textbook for the reference. The lab manual actually can be obtained in this link. And as I mentioned, I can upload to you later. The textbook, use this. Semiconductor physics and devices. All the theories are basically based on this. All the slide content are basically based on this book. If you want to study more, then you can refer to this. Okay, so this one, I will explain through the briefly. Okay, lecture 1, lecture 2 is consists of the how do you do the basic IC fabrication. Then we will discuss about the quantum mechanics. Then starting from lecture 3 until the end, we are trying to study about the semiconductor in equilibrium. This is where we are going to study about all the energy, electron, proton, whatsoever thing. Then this one is the carrier transport phenomenon, which is mostly related to the speed of the electron. PN junction, the most significant PN junction is a diode. Then MOSFET, transistor, CMOS also related to transistor. So generally, this is where the content is going to cover everything. Okay, this is the introduction. Any questions so far? Okay, you might ask whether the assignment is the individual and or the or what or group assignment. So this one I still haven't think because I still haven't designed the assignment yet. So after I design all the assignment, I will let you know later. Okay. So today is just a first class, so I don't want to teach so many things. So we hope to end the class earlier. Is that okay? So I believe some of you may have some problem in the registering everything or registering subject, or some of you may want to take a repeat of the receipt subject. Okay, so you might be busy with that. Okay, try to use this first week to do everything. By the way, how many of you still haven't get your supervisor for the FIP? Mm-hmm. How many of you still haven't get? Okay, give me 5 minutes. I got something to do. Okay, continue. Okay, this class actually is quite I would say simple. Not to say simple because we involve a lot of the equation and the calculation. And normally all the formulas are actually given to you. Okay, you don't have to half out every single equation. So I think it's quite good to you actually because for last time, like for example, your senior has to half out every single item. But for us in this subject, we don't have to do that. Okay, because formula is given, test is open book. Okay, you know that, huh? Because under this MCO class or test is open book, exam also open book, so you can just simply refer to any formula. Okay, but also lah, the exam level will be difficulty level will be higher lah, because it's simple ma, you can refer to any formula ma. So that's why we will try to make it harder. But as long as you can follow the theory, I don't think it's any problem with you. Okay. So any question? And my class actually I'm quite a flexible person. So if you couldn't make it to the class, please let me know with a valid reason. But if you don't have any valid reason, so I cannot do anything lah. Okay. So I will allow for the 15 minutes late. Okay, 15 minutes. Let's say if our class start at 1, then until 1:15 you still can come in. Then the attendance can be taken. But if you are later than 1:15, then you better let me know what's the reason. Okay. If your reason is valid, I can still take your attendance. But if not valid, sorry lah. Huh? Okay. Understand, everyone? So everyone try to relax. Don't be stressed with this subject. Mm, by the way, this is a prerequisite. Okay. If next semester you are going to take the inter-circuit ICT, integrated circuit technology, you better pass this subject. Otherwise, if you somehow fail this subject, then you cannot proceed with this ICT. Then it might affect your graduation. Okay, so please be extra careful. Okay, normally I will try to avoid to few students, but somehow I feel student before because I don't know, some of them using a wrong formula to do everything, then makes everything gone. It's kind of waste, I would say. So let's proceed. I close this. Okay, how come I cannot close on that? Very safe. Okay, disclaimer first. So this slide is for the educational purpose. All the materials, all the image equation example used in this slide are obtained from the following source, which is the book that I mentioned to you earlier. Okay, so if anything, you can refer to that. So chapter 1 is about the basic introductory of the semiconductor. But what is that about? So what is semiconductor? When we talk about semiconductor, if you still remember all the periodic tables, Okay, I'm not sure whether I half out before. Last time we got some special way to half out everything. We half out for the first 20 elements when if I'm mistaken. Then the semiconductor is a group of the materials having the conductivity in between the metals and the insulator. To be more specific, normally the semiconductor is on the column 3, column 4, and column 5. If you refer to the periodic table, you can see that actually most of the semiconductor that we use is belong these three categories. Okay, the most important one is the silicon. Okay, this is the most common one that we use. And the other one is the germanium. Germanium is somehow is quite famous in the semiconductor. Then we also got a combination of the gallium arsenide. These two things combine together to become the semiconductor. So we got the elemental semiconductor, which means that this thing is not fixed, it's not mixed with the other semiconductor. It itself can be a semiconductor. For example, like silicon or the germanium. It itself can be a semiconductor. But somehow, some of the material, it must do the combination to be the semiconductor. For example, the gallium arsenide. So these three items is the most famous item throughout our lecture. These three items are the one that is commonly used in our lectures. Okay, so when we are talking about a semiconductor, actually all the semiconductor is based on the solid. Okay, just imagine semiconductor, for example, silicon. One silicon, actually, let's say imagine silicon as a sand. We know that actually sand is made out of silicon also. Okay, inside the sand, for example, inside the sand, we know that one of the tiny material, it consists of a lot of the atom. Okay, a lot of the atom. Okay, so but all the atom in the different semiconductor, they may have the different structure. For example, this solid, the structure is like this amorphous. Amorphous means that actually the atom inside, you can see it allocate randomly. It didn't have a specific pattern. Then we also got the solid with the very regular structure. For example, this one, single crystal. All these are regular one. All these are in one line, one line, one line, one line, one. Then we also got the polycrystalline. Polycrystalline means that this semiconductor, this solid, it may have a different portion. In this portion, all the atoms are aligned this way. But in this part of the atom, all the atoms are aligned in this way. Then this one, different diagonal one. Then this one, it randomize it. So this is type of the solid. And in our lecture, we use the most common one, which is a silicon, because we want to make our life easy. Okay, how do we say that it make our life easy? So let's see. There are three types of solid. Amorphous have order within a few atomic or the molecular dimension. With this, you can see that they don't have any specific pattern. But the polycrystalline, it have a high degree of order over many atomic or molecular dimension, which means that in the different region, they have a different type of the arrangement. Single crystal, very easy, high degree, then all are the regular. Then each type is categorized by the size of the order region within the materials, which means it depends on the arrangement of the periodicity. Okay, but this one is not important. Most important that you need to know is we normally use the single crystal to be our semiconductor element. Why? Okay, the single crystal region are called grain and are separated from one another by the grain boundary, which means that here, this thing we call as a grain boundary. Okay, so in this course, we focus on a single crystal because it's better than the polycrystalline one. Because the grain boundary, it may degrade the electrical characteristic. Just give you an example. In the semiconductor, why is it a semiconductor can become semiconductor? Because the electron can flow. Okay, but somehow, let's say, imagine if you want one of the electrons somewhere inside here, electron, you want to jump to be here. The boundary may have blocked it. Okay, then this will affect the semiconductor properties. But in this, you see that this thing, nothing can block him. There's no boundary for him to block. So you can jump here, over here, no problem, jump over here, no problem. So that's why we tend to use a single crystal to become our semiconductor. Okay, any question for this? Any question? If no there, no there. Okay, let me drink water first because non-stop talking. Okay, let's proceed. So let's learn some terminology. Okay, so all these are actually the atom. Also, we call it as a lattice point. Same thing, okay? So you can refer to either lattice point or the atom. Then this one actually is a 2D pattern, okay? You look from this direction, okay? So this one is a B1 and the A1, two different direction. But it's somehow, if you try to arrange it in the 3D direction, you can see that actually it can be arranged in this way. But actually this small block actually refer to this here. Okay, this surface. So imagine if you have a multiple block here, multiple block here. So you can try to expand it. Okay, keep expanding. Okay, if you keep on extending, then escalate everything, then it will become a big semiconductor, just like a sand. But back to the most simple one, simplest one. Move everything. Okay, sorry, my computer hang already just now. Okay, let me restart the slide. Okay, so the most simple one, we just take one cell. We normally call it as a cell. Okay, one unit cell. This one, refer to here, one unit cell. So a unit cell is a small volume of the crystal that can be used to reproduce the entire crystal. What does it mean? Which means that actually it's trying to combine everything on here, nothing much. Then combine, keep combining until it become a whole map. Okay. Then here everything you will be having an atom. Atom here, atom here. Atom, 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 atom here. Every corner will have an atom. Okay, so this is a 2D, this is a 3D. Okay, then they also got a three basic crystal structure. By the way, have you ever learned about this before? This one is a simple cubic. This is a body centered. This is a face centered cubic. Have you ever seen this diagram before? Okay. I believe you guys learned about this, I think, from either chemistry or something else. But what's these three things item difference? Let's copy this to here. Okay. The most one is the simple cubic, most simple one. Simple cubic, SC. So in this simple cubic, every corner will have one sphere. Sphere. Imagine that this is a ball. Okay. Then you got an A. Imagine that A is a length. Okay. We also call it as a lattice. Sorry. TTIC constant. Okay. So this is a simple cubic. Inside there, nothing. Then this is a body-centered cubic. Okay. So in this body-centered cubic, it also the same like the simple cubic. For the every corner, they will be having a sphere. One ball here. 7, 8. Then inside got one more ball. Okay. This thing we call it as a body-centered cubic. Then face center cubic. Face center cubic, same thing. Every corner will have one, but inside they don't have any. Then at the surface here, they will have one ball here. 1, 2, 3, 4, 5, 6. Also, they are also having the same distance, that is constant A, and A. Okay, before I proceed, can anyone tell me, based on this diagram, simple cubic, how many atoms do you have if you consider this eight corner? Okay, let's have a guess first. Open quiz. Okay, for the, let's say this one, how many atom? Number of atom. Some say two. Any other answer? Any other answer? Some say one. One. How many of you say one? Okay, maybe I create a pool. Then I see how many of you can vote. Let's start a pool. Then, how many atoms? One or two? Save it. Then let's vote and see what happened. Everyone, go to vote. And let me see what is the result about for this. Launch. Okay, let's vote. Okay, 2 vote go to 1. 8 vote go to 1. 13 go to 1. Wait, you all back out one away. Seriously? 18 go to 1. 19 go to 1. 23 go to 1. 24. Well, looks like you all back out already one. Okay. We still have a 6 vote. 25. 5 more vote. Okay. 1. 27. Okay. I think a few more vote, right? Three more percent. 28. Okay. 2 more vote. Any more people here? Okay. Then let me end the poll. I assume everyone has voted. End the poll. So most of you say 1. Yes, the answer is 1 for this. Why does we say 1? This is 1. 1 atom. Yeah, 1 atom. Imagine this is a ball. Then somehow you only share one corner here. Okay, you share one corner here only. You share one corner of this. Okay, you share this corner in this region. Okay, share one corner, part of it. Okay, so this is a 1/8. Okay, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. This must be 1/8 only. Sorry for the ugly writing. Then we are trying to multiply 8. You will get 1 atom. So in the simple cubic, you only have 1 atom. So let's try. Second one. Let's create another poll. How many atoms for this and the cubic? Cubic, sorry. So you can 1, 2, 3, 4, 5. Okay, let's launch it for the second one. See how many do you have. Okay, we got a 6, 8, 11, 13, 15. Oh, very fast, huh? Okay, what about the rest of you? Let's see. 20, 22, 26. Okay, a few more people. 27. Any more? By the way, don't worry if you want to have a different opinion, just WhatsApp. We'll see whether it's correct or not. Okay, 28. I think they are supposed to have another 2 more people, right? So show everyone the result. So there are 28 posts, 28 work actually. So let's see. So just now, the symbol cubic, we have a 1, 1, 1. Okay, all these are 1. So right now, we know that if we tumble all the 1 corner together, it becomes 1 atom. Then plus another atom in the middle, total is 2 atoms. So 2 is the correct answer. So good one, everyone. Everyone can get the correct answer. So let's try to create the third one. Okay, how many atoms? 4 face centered cubic XCC. Same thing, 1, 2, 3, 4, 5, 6, 7. Okay, launch. Show code. Okay, start to work. Okay, this is quite interesting right now. Right now we have a different opinion. Some say 7. Interesting. 22. 22 what? 23. 26. So yeah, 6 would go to the 7 atoms. Then 17 would go to the 4 atoms. 2 would go to 3 atoms. 1 would go to 2 atoms. There are 2 more people haven't worked yet. So let's see. We wait for another 2 guys. 3. Somebody go to 3. Okay, 1 more guy. 18. Yep. So let's see who is the correct one. This one, we focus on this here. This one only. Okay, let me drag. Same thing happened here. Corner 1, we know that there's a 1 atom. What is surface 1? Okay, in the surface, actually, this is a sphere. It cut into half. Okay, in every single surface. Okay, inside got half. Then the one opposite to it, another half. Okay, half plus half is 1. Okay, so we know that for 2 surface will become a 1 atom. These 2 surface will become 1 atom. 1, 2, and 3. So eventually, we know that we are having the 1 plus 3 atom, which is total up to the 4 atoms. So the answer is 4, and most of you can get it correctly. Thank you very much for your participation. Okay, any question for this part? Any question? If no, then that would know that. So I believe most of you don't have any question. Okay, very good. Seems like everyone can understand it. So let's proceed. So after we know that what is the number of the atoms in one unit cell, then we can calculate the volume density. But what is the volume density? So basically, volume density is the measurement of number of the atom in the one volume. So in short, for example, this, you can see that number of the atom in one unit cell. So for example, you are having a simple cubic. We only know that this simple cubic will have 1 atom. Then we also need to calculate what's the volume. Volume is based on the lattice constant. In this case, we can use the formula 1 divided by A cube, something like this. Okay, so this is the volume density. Then let's see some example. Okay, find the volume density of the atom in the simple cubic given the lattice constant is equals to 5A. But you can see this A above there is a small circle over there. What does it mean? Which means that whenever you can see this small a, it equals to 5A circle equals to 5 times 10 to the power of negative 8 cm, or equals to 5 times 10 to the power of negative 10 meter. Okay, if you want to be short, you always remember this A equals to this. Okay, remember this because we will keep using this. So imagine if this lattice constant is equals to 5A times 10 to the power negative 10, A equals to 5 times 10 to the power negative 10, and find the volume density. So to find the volume density equals to the number of the atom. So this is the simple cubic. One atom divided by 5 times 10 to the power of negative 10 to the power of cube. Okay, then this will give you the answer of 2 times 21 to the power of 21 atom over cm cube because I'm using the negative 8. If you are using the negative 10, this thing have to be in the meter. Okay, common sense. Okay, let's try another example. Find a volume of the density of the atom in the body-centered crystal given the lattice constant is equals to 5A. Okay, right now, try to use a pen and a pencil and try to calculate what is the answer about. Okay, let's start. So after done, type your answer into the chat box. Okay, some of you get 1.6 times 10 to the power of 28. What about the rest of you? Anyone? Okay, what about the rest of you? Yongqi, what's your answer? So I expect somebody can reply me, otherwise I will keep on randomly asking someone to answer me. Okay, this is my style. Just get used to it. How come my answer so weird one? Okay, so let's see. I know why. It's kind of about three. Okay, since most of you can get the same answer, uh, the CM3 or M3 is depends on which one you use in the below one. If you are using 10 to the power negative 10, then you are using M to the power 3. Okay? Okay, how many of you can get this 1.6 times 10 to the power negative 28? Are you able to get this answer? Okay, cool. We take a 5 minute short break. After that, 10 minutes short break. After that, we come back. Okay? Hello, everyone. Shall we proceed? Okay. Let me know if you couldn't follow so that I can slow my speed. Sometimes I can speak too fast and you cannot catch up. And please let me know so that I can reduce my speed and we can adjust accordingly. Okay. So let's see this. Here's another example that we're going to deal with. Let's see what's the example about. The volume density of an atom for a simple cubic is 3 times 10 to the power of 22 cm minus cube. Assume that the atoms are half sphere with each of the atom touching its nearest neighbor. Determine the lattice constant A and the radius of the atom R. So it's given one thing, and then it's saying that for this simple cubic, all the atoms are touching each others, which means that originally, when we saw the simple cubic is like this. All the dots are here, dots are here, dots are here, dots are here. But somehow, this simple cubic, all the atoms are very big. Okay, this atom are very big, this atom are very big, this atom are very big, until both of them touch each others. Then he asks you, okay, to calculate the lattice A, A, A. He wants to calculate where's the A. Then after calculating the A, we need to know what's the radius of the atom. So this one is kind of relatively simple as the answer is given. And based on this, this one is a simple cubic. So VD equals to 1 over A cubed. We know that the atom is only one satu biji saja. So 3 times 10 to the power of 22 cm minus cube. So this one is calculated in cm. Okay. So equals to 1 over cube. So 1 cube equals to 3 times 10 to the power of 22. So eventually, after all the calculation, we can know that the A is equals to 3.22 times 10 to the power of negative 8 or negative 8. Should be 8, right? Let me check back. Okay, negative 8. Negative 8 cm. Because this value are calculated in cm. So your A, your lattice constant should be in the cm also. Okay. Then we know that in short, A equals to 3.22 A. Then the R radius is A divided by 2. Why? Because both of the atoms are touching each others. Then from here to here, we can know that this is A. Okay? This one is R, this one is R. Both are having the same radius. So we just need to divide it by 2 to get our final value, which is 1.61. This one. In this case, can you understand this? Boleh faham tak? Okay, two of you say okay. What about the rest of you? Or you need me to re-explain again? Please let me know. Otherwise, everything I need to open the poll for you to work whether I can understand or not understand. Radius for others layout. Okay, this is a very good question. We are going to discuss it later. Okay. So let's proceed. Okay, before we proceed to the other layout, okay, we need to discuss what's the crystal plane and the Miller index. So since the actually one unit cell is a very, very small, you can see that from the calculations just now, we can see that the value can be go to 10 times 10 times 10 to the power -8 -10. So normally the semiconductor are fabricated on the near surface. Then the surface may influence the device character. Then surface or the plane through the crystal, we normally need one way to describe what's the surface about. Okay, what does it mean? So normally, for example, like this, in this case. Okay, so imagine this one is an atom, atom, atom. All these are the lattice point. Okay, so we somehow need to use this surface on it, but we need to figure out a way to explain this surface. How are we going to explain this? Normally, we need to use all these 3 points to help us to explain what's the surface. But how are we going to explain? Let us remove all these things first. So we go from this direction, 1 second, and the third, 1, 2, and 3. So in this direction, we know that there are 3 points. 1, 2, 3. P equals to 3. And then in this direction, 1, 2. Q equals to 2. P, Q, X. Okay? Then X equals to 1. Okay? 3, 2, 1. So in order for us to describe this, one guy, he called a Miller, he purposely create a troublesome way to describe it. But how? Okay, so he used all the reciprocals. P equals to 3, Q equals to 2, S equals to 1. Then he divide everything by 1. 1 over 3, 1 over 2, 1 over 1. After that, he multiply everything until a whole number instead of a fraction. So in order for you to turn everything into not a fraction and integer, you need to multiply 3 first, right? So let me write here. Okay. So at first we put 1 over 3, 1 over 2, 1. So at first we multiply 3 equals to 1, 3 over 2, 3. But instead of 1, 2 here, multiply by 2. 2, 3, 6. So eventually he used the value 236 to explain this plane. So whenever when people mention the plane 236, this means that it refers to this plane. You might want to ask why you don't use directly the 321. What's the difference? Because sometimes your surface can be like this. For example, this. Okay? Let's see this. Okay, in the P direction, this direction are P. Wait, let me draw it. P, Q, and X direction. P direction, we know that the atom is 1. Okay? P equals to 1. But in the Q direction, can you see where does it? This direction. Okay? So this is a P. All P are intersect in this point. Okay. Q. Somehow Q here. Okay, intercept. No, this surface. This surface, he didn't intercept any of the point here, right? He didn't intercept any P, any Q here. He just threw it out here only. He is parallel to the Q. You know Q is the infinity. Okay? What about the S? So S is also going outward. Going outward. It didn't intercept any point. Actually, you can see it didn't intercept any point. So this is towards the infinity. So somehow, Miller index is to avoid the infinity. Okay? So we write this reciprocal 1 over 1, 1 over infinity, 1 over infinity. 1 over infinity equals to what? Equals to 0. So that this can be discussed as a 100 plane. Okay? Or you can imagine saying like he didn't intercept to any point. So that's why there's an O. So that's why people, Miller, he tend to use the reciprocal. Because sometimes your brain, it didn't intersect to any. For example, this one, it didn't intersect to any Q point here. And in upward, it didn't intersect to any S point. So that's why people use this reciprocal to describe the plane. Okay, so that every time you will say one infinity plane, so long, wasting your time. So you just say one O plane, then people can directly know. Okay, this part, can you understand? Okay, oh, this part. Let me, okay. Okay, let's try another, these two examples, one, two, three. Maybe this. Okay, try this, and this. Then see what's the result. Okay, let's start with the first one, this part. Can you tell me what's the Miller index? Okay, let's pick some guy to answer. Okay, 流動量，流動量 is it? Are you here, 流動量? Yep, your friend saying 211. Others, you get the same answer. Jungqie, what do you think for this one? Oh, 流動量 is a 4.0 啊。哇，so pandai ah. Okay, 211. Others, do you agree this one is a 211? Lim Yongfan, are you here? Mr. Lin Yongfan. Okay, three of you giving me the answer 211. So let's see. P equals to 1, Q equals to 2, then S equals to 2. So this is 1 over 2, 1 over 2. Then all you need is to multiply 2. So your final answer is 2, 1, 1. Okay, simple and direct. What about this? So, Koi Chia Wen, Brenda, are you here? Let's see this. The third one. Brenda Koi. Brenda, are you here, Brenda? Why she seems missing already? Okay, let's pick another guy. Where else? Lim Chun Wei. Are you here, Lim Chun Wei? Okay, 110. Others, do you agree with the 110? Okay, kind of simple. This thing is quite direct, actually. So P equals to 1, Q equals to 1, then S equals to the infinity. Okay, so 1, C equals to O. Okay, the last one, this is quite simple. 1 only. Everyone agree? This one. Okay, let's proceed. So, just now we calculate the volume density. Right now, we can also calculate the surface density using the following formula. So, very simple. Just now is number of the atom in one plane over the area of the plane. Okay? So, for example, just now is the VD, is the number of atom divided by A to the power cube. But for this surface density, number of atom in the plane divided by the area of the plane is square. Okay, just for example, this one, calculate the surface density. Consider the body center cubic structure and the 110 plane shown as below. Assume the atom can be represented as half sphere with the closest atom touching each other. Assume the lattice constant is the A equals to the 5A. How are we going to deal with this? All he asks you is calculate the surface density of this region. Okay, he show you that all these things are touches in this way. But how are we going to deal with this? So let's see. Okay. So 110 plane. When we are talking about 110 plane, it looks something like this. Let me go here. Okay. 110 plane. At first, we need to calculate what is the number of the atom. So number of the atom. We know that in the middle there must be a 1 plus corner, 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 corner. 4 corner jumble together become 2 atom. Okay. Then you need to calculate the surface density. In order for us to calculate this surface, here. Okay, this one. Surface is somewhere around here. This surface, this one. So we need to know what is the length of this. So in order for us to find the length, we need to use the theorem particular. So let's say this one is the A2. A2 equals to A1 square plus A1 square then square root 2A1 square root. So this one is square root 2A1. So in this case, we can know that this surface is A1 square root 2. Okay? And then he asks you to calculate the surface density. Surface density. So we know that the number of atoms is 2 divided by A1 multiplied by A1 square root 2. Okay? So this one is A square multiplied by square root 2. A1 square. A1 is given in the question 5. So all you need to do is replace the 5 times 10 to the power negative 10 meter to get the final answer. So let's see if this is a cm. So this is using a cm. Okay. So after you calculating everything, ding dong here, your answer is 5.66 times 10 to the power 14 atoms square per cm square. Atoms per cm square. This part, do you understand this? Okay. The rest of you, we got about 30 people here, but only 3 people reply me only. Okay. Thank you for your reply. Yo, Brenda, welcome back. Where have you been just now? Okay. So let's try one more example. Okay. So let's see. The phase center cubic structure is this 4.25A. Calculate the surface density of an atom for A 100 plane and B 110 plane. Okay. So let's see. So 100 plane, we know that 100 plane is somewhere around here. Okay. Just now we already demonstrated. It looks something like this. This one is a 100 plane. This one, the middle one, the second one. So we just know that this is the here, 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 here. And then it also mentioned that this is the phase center cubic, which means that in the middle, there are one more atom here. Okay. So calculate the surface density. Give me a moment. Give me a moment. Sorry, I just now got something come puzzle. Okay. So let's come back to here. So lattice constant of a phase center cubic structure is 4.28, 4.25, which means this is a 4.25. Here is a 4.25. Calculate the surface density of atoms for this plane. Okay, 1 over plane. So in this plane, if you want to make it bigger, all these things must be touched together. These, oh, sorry. Let me crop this, edit this. Space, okay. Put here, and put here, and put here, here. Okay, it should look something like this. You might be wondering, why just now the thing, it look all compact together. Okay, this thing touching it like this. But right now this one, I draw in this way. Because one unit cell, both of this size and this size should be the same. So that's why I cannot draw in this way. I cannot draw in the original way, this way. Because if we draw in this way, this A will not be equal to this. I must find a way to make sure that both are having the same distance. So this is the right way to draw it. These two things should be close together. Sorry, I draw a little bit chart. Okay, 4.25 and 4.25. Okay, also same thing. I draw this, 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 this. Okay, and then right now, so this one, how many atoms? In between one atom, 1, 2, 3, 4, 2. Okay, 1 plus 1 equals to 2 divided by 4.25 times 10 to the power of negative 8 squared to give us the final answer. Okay, so this one I left you to calculate. The next one, what about a 110 plane? Let's see 110 plane. 110 plane should be something like this. Okay, 110 plane should be something like this. So let's see what does the 110 plane looks like. So right now, 110 plane. So it looks something like this. Here, 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 here. Okay? So right now, here also A, here also A. And here is also the square root 2A. Here's the A. But if we get close to each other, all these things only have one atom. So the final answer should be A squared 2. Okay? So in this case, you put 4.25 times 10 to the power of negative 8 squared multiplied by square root 2. So in short, when open, your surface density equals to, you have a 2, 4.25 times 10 to the power of negative 8 squared. This one is in cm. So for the one open, then your surface density, only one atom, then you have to 4.25 times 10 to the power of negative 8 squared, then multiply square root 2. Okay, let's calculate the answer. Let me draw here. And give me what's the final value. So after calculating this, then we can end the class for today. Okay, Wong Chun give us the answer already. What about the rest of you? Let's cross check if you can get the answer correctly. Let me calculate on my side also. Okay, the first one I can get is 1.10 times 10 to the power of 15, as shown by Wong Chun Yi. So let's me complete the next one. 1 divided by 4.25. Yep, I get 3.914 times 10 to the power 14 for the second one. The rest of you, do you get the same answer? You can just don't simply type a yes over there. I must calculate one. Okay? Don't simply just type a yes over there. I tell you. Okay. Brenda, where are you? Tell me your answer, Brenda. So pandai, type the same there. Okay, so basically this is the way that we calculate all the answers. So any questions so far about this? So for the all the following thing, I think I will mention in the next lecture. Okay, it's all on the fabrication things already. Okay. So any questions so far? So if no question, then shall we end the class for today, everyone? Okay, I think we end the class earlier today. Since this is the first semester, first class, so we relax a bit first. No worry about it. Okay, I will see you by the next class. Thank you very much for your time. Have a good day. Bye, everyone. Thank you. Yes, I believe we have a tutorial class this week. And see your timetable. The timetable is according to your tutorial. Okay, depend on your group. Okay, I'll see you next class. Thank you, everyone. Have a good day. Bye, everyone.